Hey everyone, welcome to the second week of General Chemistry 2 this second semester, and our topic for this week will be all about intermolecular forces. So what is the difference between intramolecular forces and intermolecular forces? Intramolecular forces hold atoms together within a molecule, while intermolecular forces are attractive forces between molecules. So to explain it better, let's take water as an example. So your idea about how to draw Lewis structures will also be applied in here. The steps in drawing Lewis structures were already introduced during General Chemistry 1. So we try to draw the Lewis structure of a water molecule, which is H2O. Okay, so the intramolecular force, by definition, it's found within a molecule. Therefore, the intramolecular force is found on the hydrogen-oxygen bonding. So this is your intramolecular force. It's within the molecule. Intermolecular force will take place if another water molecule will be brought near it. So if another water molecule will be brought closer to another water molecule, then the intermolecular force will be found in here. So intermolecular force is found between two or more molecules. And this is what we are going to study for this week. If you are familiar with the ionic and the covalent bond, then those two fall under intramolecular forces. So here are the types of intermolecular forces arranged from strongest to weakest. First is the ion-dipole force, followed by the hydrogen bond, then the dipole-dipole forces, and lastly, the London dispersion forces. First is the ion-dipole forces. These are attractive forces between an ion and a dipole. And dipole moments are only exhibited to polar molecules, or they are only present to polar molecules. So we have here two important terms. We have ion and a dipole. An ion, just a review, is an atom with a net charge. It may be a positive or negatively charged ion due to the loss or gain of electrons. And when we say dipole, this is a molecule that carries two opposite charges separated by a small distance. So based on the name itself, it's a dipole, meaning to say one end of it is positive, the other end is negative. So by illustration, the ion-dipole force is just like this. An ion, either negatively charged or positively charged, will be attracted to a polar molecule with a dipole moment. So one end is partially positive, the other end is partially negative. So opposite charges attract. So for an ion, it will be attracted to the partial positive charge of the polar molecule, and the cation will be attracted to the partial negatively charged side of the polar molecule. So here is the trend of the charges of the elements in the periodic table. You may take a picture for now because we will be using these charges for some of the examples afterward. So an example for ion-dipole forces. What will happen to sodium chloride when you place it in water? Now sodium chloride, or NaCl, or simply the salt, when they are dissolved in water, they immediately dissociate into two ions, the sodium ion and the chlorine ion. Take note, NaCl is an ionic compound. So this is now a picture showing you the ion-dipole interaction of the solid ionic crystal when dissolved in water. So the arrows in here indicate the ion-dipole interactions. So again, when salt is dissolved in water, the sodium chloride will immediately dissociate into two separate ions, the sodium and the chlorine. So where is the ion dipole force in here? So we just simply put the first ion, which is the sodium, which is partially positive. So where did we get this partial positive charge? By the way, we use the delta symbol in Greek to represent the partial charges of the atoms. Sodium in here is partially positive. Based on the table, it belongs to group 1 and group 1 has positive 1 charge. No need to write the number. And then the polar molecule here is the water, so we draw the water molecule's Lewis structure. Okay, so we also assign the partial charges of H2O. So based on the table, oxygen is partially negative while hydrogen is partially positive. Again, opposite charges attract, so sodium will be attracted to oxygen, which is negatively charged. So here is now your ion dipole force. The other ion is the chlorine ion, negatively charged. Again, you draw the water molecule's Lewis structure. Oxygen is negatively charged. Hydrogen is positively charged. So chlorine in here is negative, so it will be attracted to hydrogen. So here is now your ion dipole force. So ion dipole force is just easy. If you have an ion plus a polar molecule, then ion dipole forces is present in this situation. Another example, which of the following molecules will create an ion dipole interactions with the nickel positive 2 ion? So the ion in here, the cation, is already given. So we are looking for a polar molecule among the choices. So if that is a polar molecule, then definitely that is already the answer because polar molecules exhibit a dipole moment. So for letter A, it's a diatom of hydrogen. It's a dihydride. And take note, all diatoms are automatically non-polar. So this is not the answer. For carbon dioxide, we try to draw the Lewis structure for us to determine its polarity. So carbon dioxide's total number of valence electrons is 16. So if we are going to draw the Lewis structure, it will be this. Okay, 2, 4, 6, 8, 10, 12, 14, and 16. So as I recall, when the central atom does not have any lone pair, then that is a nonpolar molecule. If it has a lone pair, that is a polar molecule. So in carbon dioxide's case, this is a nonpolar molecule, hence it's not the answer. For CH4, the total valence electrons is 8. So the Lewis structure will be C with 4 hydrogen atoms. Again, carbon as the central atom does not have any lone pair, so this is also a non-polar molecule. Lastly, the SO2, the total valence electron is 18. So if you are going to write the Lewis structure, it will be S as the central atom, 2, 4, 6, 8, 10, 12, 14, 16, 17, and 18. As you can see, the central atom has a lone pair, then therefore this is a polar molecule, and this one is the correct answer. So where can we find now the ion dipole force between the nickel positive 2 and SO2? So we write the given, Ni positive 2, and then the Lewis structure of SO2. So we assign also the charges of sulfur and oxygen. Okay, so as you can see on the table, they belong to the same group. So how are we going to determine if which of them is partial positive and which of them is partial negative? So if you can still recall the trend of electronegativity in the periodic table, then that definitely will answer our question. From bottom to top, there is an increasing electronegativity. That means to say oxygen is more electronegative than sulfur in this case. So oxygen therefore will be partially negative and sulfur will be partially positive. So since nickel is positive 2, it will be attracted to oxygen which is partially negative. So this is now your ion dipole force. Next type of IMF is the hydrogen bond. This is a special and stronger type of dipole-dipole interaction. So hydrogen bond is very simple or easy to determine because if hydrogen is attracted or attached to either nitrogen, oxygen, or fluorine, then that is a hydrogen bond. So why is it a stronger type of a dipole-dipole force? So the reason is that the strength of the hydrogen bond is due to the small size of hydrogen and the large electronegativity of NO and F. So since NOF are much more electronegative than hydrogen, the dipole is stronger, and when the dipole is stronger, the polarity is also stronger, and when the polarity of the bond is stronger, the bond is also stronger. So that makes hydrogen bond stronger than the usual dipole-dipole force. Okay, so we have here an example of H2O. So one water molecule is bonded to another molecule. Since hydrogen is bonded to O or oxygen, it shows therefore a hydrogen bond. Another example, which molecule exhibits H bonds? So it's very easy to determine. Once hydrogen is either attached to N, O, or F, then it exhibits a hydrogen bond. Okay, so it's not just enough to just look at the molecular formula of the molecules. So it's very important to draw their Lewis structures because even though they have hydrogen or fluorine in their molecular formula, we are not sure if they are bonded in their Lewis structure. So we try to draw this one. So CH3CH4, CH3F, if you are going to draw its Lewis structure, it will look like this. Okay, so as you can see, carbon in here is bonded to hydrogen. So hydrogen and fluorine are not attached with each other. Therefore, CH3F does not exhibit a hydrogen bond because H and F is not attached with each other. Letter B, we have the CH4. So we draw the Lewis structure. CH4. Hydrogen is not attached to NOF. Therefore, this is also not a hydrogen bond. Letter C is HF. Just by looking at it, there is no other atoms in the molecular formula. Then HF simply exhibits a hydrogen bond. So hydrogen and fluorine. And lastly, the CH3CHO. So we have Lewis structure, C, and then H, and then O. So as you can see, hydrogen is bonded to carbon and not to oxygen. So CH3CHO does not exhibit a hydrogen bond. So the correct answer, okay, so we still have one. We have the NH3. So we draw N and then 3 hydrogen atoms. So hydrogen is bonded to nitrogen. So this one exhibits a hydrogen bond. So the answers are letter C and letter E. The third one is the dipole-dipole force. Dipole-dipole forces are attractive forces between polar molecules because polar molecules exhibit a dipole moment. So since polar molecules have dipole moments, meaning to say one end is positively charged, the other end is negatively charged. So dipole-dipole forces will be present once the negatively charged side of one molecule is attracted to the positively charged side of another molecule. So this is how dipole-dipole force occurs. So here is an example of a dipole-dipole force. Which of them exhibits a dipole-dipole force? So between carbon dioxide and SO2, which of them has a dipole-dipole force? So in order to determine their polarity, we need to draw their Lewis structures. So for carbon dioxide, the total number of valence is 16. So the Lewis structure is C, double bond with O, and then 2, 4, 6, 8, 10, 12, 14, 16. So, as you can see here, there is no lone pair at the central atom, therefore CO2 is a non-polar molecule. And then for SO2, the total number of valence is 18 electrons. So the Lewis structure is SO, and then 2, 4, 6, 8, 10, 12, 14, 16, 17, and 18. So as you can see, sulfur at the central atom has a lone pair. So that means to say this is a polar molecule. And take note, dipole-dipole forces occurs in polar molecules. So the answer is SO2. Next one is the London dispersion forces. London dispersion forces are found in every type of atom or molecule. However, they are predominant in nonpolar molecules. So, all of the molecules have LDF, but it's predominant to nonpolar molecules. Okay, so how are London dispersion forces present in nonpolar molecules? The fact that nonpolar molecules do not make permanent dipoles. So here is how LDF occurs. So as we all know, nonpolar molecules have an even distribution of electrons around their atom. Okay, so how are they going to make dipoles from this one if they have even distribution of electrons? So take note, atoms, for once in a while, they undergo several distortions. So there are times that when they are distorted, one side is electron rich, the other side is electron deficient. So if that is the case, one side will be electron rich, it will be negative. The other side is electron deficient, it will be positive. And from the distortion of the polar molecules creates temporary dipoles. So as you can see, because it already has a positive and a negative sides, but it's only a temporary dipole. So here is now the reason why LDF or LDFs are the weakest forces, weakest type of IMF, because they only make temporary dipoles. So any changes in the environment could distort back these molecules. So if one temporary dipole from a nonpolar molecule will be brought to another temporary dipole, which is a nonpolar, then the LDF will be found in here. So here is now your London dispersion force. So it's only made from temporary dipoles of nonpolar molecules. So let's try to see the relationship of the size of the atoms to LDF. So try to compare iodine and fluorine, which has a greater London dispersion force between them. So how are we going to determine the sizes of the atoms. So take note, from the periodic table, the atomic number represents the number of electrons. And the greater the amount of the electrons, the bigger the size of the atom. So between iodine and fluorine, if you can see at the periodic table, iodine has 53 electrons and fluorine has 9 electrons. So which is greater, therefore, it will be the iodine. So what conclusion can we get from here? Take note that the larger the molecule, the greater the dispersion force because it contains more electrons. That's the first conclusion. Another one, which of the following has the greatest LDF? So we are now trying to look at the relationship of LDF to boiling point. So we have here 4 elements to compare. We have the krypton, argon, neon, and helium. So as you can see, krypton here has the greatest number of electrons and helium has the least number of electrons. As to the boiling point, krypton also has the highest boiling point. Take note, the values are in negative. So the smaller the value, the greater it is. And then for the helium, it has the lowest boiling point. Okay. And it also has the least number of electrons. So what could we get? What idea could we get in here? The larger the molecule, therefore, the higher the boiling point, hence the greater the dispersion force. So if we are going to connect our first conclusion to the boiling point from this, so greater electrons will have greater boiling points. And if that is the case, it will also have a greater dispersion force or greater intermolecular force. So they are all directly proportional. So let's try this one. Before I forget, it's not only boiling point and it's not only that the greater the boiling point, the greater the LDF. It's also true with the melting points. Okay, so the greater the melting points, the greater the LDF or IMF also. So let's take this example, which has the highest boiling point. So it's F2, Cl2, Br2, and I2. So we are going to base their boiling points from their number of electrons because the greater the number of electrons, the greater the boiling point. Okay, so for fluorine, it has 9 electrons times 2 because it's a diatom, so it has 18. For chlorine, we have based on the periodic table times 2. So we have 34 electrons. Bromine has 35 times 2, that would be 70. And iodine is 53 times 2, that would be 106 electrons. So among these 4, I2 has the greatest number of electrons, hence it also has the highest boiling point. So I2 is the correct answer. Last one, which has a strong LDF based on structures. So we are now seeing in here the relationship of structures to LDF. So we have 2 different molecules in here. We have the pentane and the neopentane. So pentane, as you can see from the structure, is a straight chain structure, while the neopentane is a branched one. Their boiling point is, for the pentane, it is 36 degrees Celsius and neopentane is 9.5 degrees Celsius. Why? Why does straight chains have higher boiling points than the branched chain? The boiling point of long molecules increase with the length of the carbon chain. That's why pentane in here has higher boiling point. So, relating it from our previous conclusion that the higher the boiling point, the greater the LDF or the IMF. So what conclusion could we get in here? Straight chains therefore have stronger LDFs than branch. Okay. So let's try to do the practice problems. For number 1, rank the following in decreasing melting point. Okay, so for this one, we need to arrange them from the highest melting point to the lowest melting point. So we have 3 molecules in here, BaBr2, BaF2, and CH3CH2, CH2OH. Just by looking at the molecules, you can conclude that the last molecule, CH3CH2, CH2OH, is a straight chain. And we have just mentioned a while ago that straight chains have greater LDF or IMF. Hence, they have a higher boiling or melting point. So automatically, this one has the highest melting point. If you still want to draw the Lewis structure to determine what type of IMF it is, then that would be better. So we have CH3, CH2, another CH2, and then OH. As you can see, hydrogen is bonded with oxygen. So this one is a hydrogen bond. So this is the second strongest IMF. So it's true that this molecule has the highest melting point. Now on these two, the BaBr2 and BaF2, if you are comparing two molecules with the same atom paired within them, then you just have to simply look at the number of electrons of the other pair. So the first molecule is Br, the second molecule is F2, since they are the same paired with barium. So bromine in here has 35 electrons times 2, that would be 70 electrons, and fluorine has 9 electrons times 2, then that is 18 electrons. We have mentioned a while back that the greater the number of electrons, the higher the boiling or melting point. So between BaBr2 and BaF2, BaBr2 has a greater melting point. So if we are now going to rank these 3 molecules in decreasing melting point, so we will begin with the highest melting point, which is the CH3, CH2, CH2OH, followed by BaBr2, and lastly, the weakest one, BaF2. So this is the correct answer. Last problem, identify the strongest IMF present in each of the following substances. So in order for us to determine what type of IMF is present in each molecule, the best way is to draw their Lewis structures. So for SO3, that would be the total valence electrons is 24. So the Lewis structure will look like this. So we have 3 oxygen atoms around it with 8 electrons each. Okay, so 8, 16, 24. As you can see, the central atom does not have any lone pair, so this one is a non-polar molecule. So what type of IMF is present in non-polar molecules? The answer would be LDF. So for letter A, the answer is London dispersion force. For letter B, NH3, so we have N, H, and then H. So as you can see, hydrogen here is bonded or attracted to nitrogen. And hydrogen bonds, for hydrogen bonds to occur, hydrogen should be attracted to NO or F. So this one is a hydrogen bond. For letter C, it's H2O or the water molecule. So we have A, O and then H. And then 2 lone pairs. So this is a polar molecule. Since this is a polar molecule, dipole-dipole force is also present in this example. But the problem is telling us to identify the strongest IMF present. Therefore, the answer is still hydrogen bond because hydrogen bonds are stronger than dipole-dipole force. Letter D is PCl3. The total valence is 26 electrons. So we have P, Cl, Cl, and then another. So we complete 8 electrons each. So that 8, 16, 24, 25, 26. There is a lone pair at the central atom, hence this is a polar molecule. And what type of IMF is present in polar molecules? The answer will be the dipole-dipole force or the DDF. So letter A, answer for letter A is LDF, letter B, hydrogen bond, letter C is hydrogen bond, and letter D, dipole-dipole force. So just a recap on the 4 types of intermolecular forces. Take note that the strongest is the ion-dipole force. It is present in an ion plus a polar molecule. The second one is a hydrogen bond when hydrogen is either attracted to nitrogen, oxygen, or fluorine. The third one is a dipole-dipole force only present to polar molecules. And while the LDF, the weakest, LDF occurs to non-polar molecules. Okay, so this ends our lesson for this week. Thank you for watching, and if you want to keep updated on chemistry videos, you just have to visit the Science Saya in our YouTube. So I would like to end this lesson with this quotation by William Blake: "Without contraries is no progression. Attraction and repulsion, reason and energy, love and hate are necessary to human existence." Good day, everyone.